Okay, allow me to share my screen. Allow me to share my screen. So our topic of discussion today involves chapter 4. Okay, multiple regression model. Basically, chapter 4, or to be more specific, multiple regression model is similar to the simple regression model. Okay, but of course there are a number of additional information that you need to take into account, or that you need to be aware of when it comes to multiple regression model. But as an introduction, if I can explain the definition of a multiple regression model, basically a multiple regression model involves multiple explanatory variable. So that is where the words multiple regression came from, the words multiple explanatory variable. Yeah, it means that we have more than one independent. We have more than one X in the econometric model when we draw it in a econometric function. The reason why it is important for us to know not just single regression model or simple regression model, but multiple regression model is because many of the economic phenomena involve multiple variables, or in other words, many of the economic phenomena cannot simply be explained by one explanatory variable. Yeah, for example, when we talk about the demand of a particular product, for example, the demand of a particular product cannot simply be explained by price, because perhaps there are many other factors that are involved, perhaps brand, or maybe the design of the product, or maybe marketing strategy, maybe. Yeah, so these are the other explanatory variable that can influence the dependent variable. Based on example, the demand on a particular product. So this is just an example, and there are many other examples that we can that we can find as well apart from that. So that's the reason when we wanted to analyze an economic phenomena, we cannot simply look into one independent variable or one explanatory variable. We have to take into account multiple explanatory variable. So in this chapter, there are a number of points of discussion. First is we will try to see how to estimate the multiple regression model. Of course, that's the most important thing for us to discuss today, to see how we can estimate the multiple regression model. Apart from that, we will also be discussing about how to conduct the hypothesis testing. If you can still remember, in chapter 3, we discussed about the hypothesis testing for simple linear regression. Hypothesis testing means we are trying to determine whether we can accept the estimation of a regression model or to reject it. Okay, so that is basically a brief explanation or definition of a hypothesis testing in regression model. And of course, apart from that, we will also be looking into the unique features of multiple regression model. Yeah, so these unique features will help us to understand the difference between multiple and simple regression analysis or regression model, apart from the fact that in a multiple regression model, we have more than one explanatory variable. Okay, so what you see on the slide in equation 4.1 is a 3-variable population regression function. in a non-stochastic form. Remember, non-stochastic form of a population regression function or any regression function means that in the econometric function, or in that particular regression function, we did not include the error term. So just like in equation 4.1 here, the expected value for y equals beta 1, which is the intercept, plus beta 2 x2, b2, or beta 2 in a population, refers to the slope of that regression line. When we draw the line and we measure the slope, that slope is indicated on the value of this beta 2. And then here you can see that we have more than one explanatory variable. So that is why, apart from the beta 2, we have beta 3 x3 as well. Yeah, so beta 3 represent the slope of a regression line for this additional explanatory variable x3. Yeah, so here you can see we have two explanatory variables, two independent variables, yeah, x2 and x3. In a simple population regression line or simple population regression function, we only have one x indicating one explanatory variable. But in this case, we have more than one. So in this, to be more specific, in equation 4.1, we have two independent variables. So this is the simplest form of a multiple regression model. Simplest form of a multiple regression model where we have three variables, two independent variable and one dependent variable represented by y here. Okay, so this is to make it more easy for you to understand, we select three variables. But of course, in reality, we may have more than that. Yeah. Okay, so when we include the stochastic form or the error term, we can create this equation 4.2 here. Yeah, where y, which is the dependent variable, equals beta 1 plus beta 2 x2 plus beta 3 x3 plus error term. Okay, so this beta 1 plus beta 2 x2 plus beta 3 x3 is the systematic component of the population regression function, and it can also be represented by EY, because this here is the same as equation 4.1. They are the exact same component, beta 1 plus beta 2 x2 plus beta 3 x3. And in this population regression function, we also have this stochastic component, yeah, or the error term component, represented by mu. Yeah. Of course, the T here refers to the number of observation. As we all aware, okay, the mean value of the dependent variable, okay, will be different depending on any given value of the independent variables. Okay, so that T represent the number of observation, for that particular y. Okay, for that particular dependent variable, given a value of the dependent, given a value of the independent variable. Okay, I'm not going to explain much about the basic informations of the multiple regression function or the multiple regression model, because my main focus in this lecture will be to show you how we can estimate the key informations of a multiple regression model. Means that I'm going to show you how do we estimate beta 1, beta 2, beta 3. But of course, we will never be able to estimate the actual value of beta 1, beta 2, beta 3, but we have the estimator, which will be the B1, B2, B3, together with the other important information for hypothesis testing as well. So the rest, try to spend time, if you have the textbook, try to read more on the textbook. for essential econometrics to learn more on the multiple regression model. Okay, so remember that these beta values, which we also called as coefficient, they are called partial regression coefficient. Beta 1, beta 2, beta 3, for example, they are called partial regression coefficient. And the reason why we call them partial regression coefficient is because, or partial slope coefficient, is because this coefficient shows the rate of change of the dependent variable per unit of change in the independent variable in a particular independent variable holding the other independent variable constant. For example, B2 measures the change in the mean value of the dependent variable, okay, per unit of change in X2, holding the value of X3 constant, and likewise for beta 3. So that is why we call them as partial, partial. And here you can see the assumptions of a multiple regression model. So here it is clear that the assumption for multiple regression model is pretty much the same as in the simple regression model. We have 7 assumptions. Assumption number 7 is important for hypothesis testing. So assumption number 1 is that the regression model is linear in its parameter. Linear in its parameter, the regression model. So that is why we call them as linear regression model. Assumption number 2 is that the explanatory variables, X2 and X3, based on our example for three explanatory variables, sorry, the three variables of a multiple regression models. The X2 and X3 are uncorrelated with the disturbance term. Means that X2 and X3, they are not correlated with the error terms. Okay? They are not influenced by the error term. Assumption number 3 is that the error term mu has a zero mean value. So the expected value of mu or error term is equal to 0. This is very important. Just like what I have shown you in chapter 2, where when we calculate the value of the error term, that error term in its value is equal to 0. In its average value is equal to 0. So assumption number 4 is that the variance of the error term is constant or homoscedastic. Means that the variance in its distribution around its mean is similar across all value of the independent variable, across all axes. The distributions of the error term around its mean value across all explanatory variables will be constant. Their shape will be the same across all axes. This is just like what I have shown you in chapter 3. Okay, just like in a simple regression model. Assumption number 5 is that there is no autocorrelation between the error terms. We need to keep in mind that error terms are varied. Error terms are varied. So we may have different error term for a different for a different explanatory variable values. But the relationship between these error terms is 0, means that there is no autocorrelation between them. One error term for a particular observation is not the same as the error term in a different number of observation or in a different observation. So here we have the error term in observation I and error term at observation J. Okay, so their covariance is equal to 0, and the I observation is not the same as J observation. So that's assumption number 5. Assumption number 6 is that there is no exact collinearity between X2 and X3. Apart from the fact that X2 and X3 are uncorrelated with the error term, or disturbance term, the explanatory variable themselves are not correlated to one another. Means that x2 is not influencing x3 or has no relationship with x3. Same goes to x3 is not influencing or not influenced by x2. Okay, this is very important in order to ensure that our estimation is free from what is known as a multicollinearity. Okay, and assumption number 7. Assumption number 7 is that the error term mu follows the normal distribution with zero mean and constant variance. So here we have the error term, which is normally distributed with zero mean. Okay, so this zero mean is just the same as in assumption number 3, with a constant variance represented by this sigma square. Okay, so the variance is constant, just like as mentioned in assumption number 4. Reason why we need assumption number 7 is because when we conduct the hypothesis testing, we need to ensure that the explanatory variable themselves follows a normal distribution. Okay, they follows a normal distribution. How do we know that they follows normal distribution? It is because the error terms follows normal distribution. Only by then we'll be able to conduct the hypothesis testing, by assuming that the explanatory variable follows the normal distribution. But remember, normal distribution is applied for a population. And in analyzing or in conducting the regression model, we may not be able to gather the entire population in information or to gather the entire data in a population. So we have to rely on the sample. And these samples follows the t distribution. And that t distribution, okay, that t distribution help us to determine whether, help us to conduct the hypothesis testing. So we need to assume that the sample follows the t distribution. Okay, we need to assume that the sample follows the t distribution. So that sample follows the t distribution as if the what we call as the population in terms of explanatory variable also follows the normal distribution. And we know that the population for the explanatory variables follows the normal distribution because the error term follows the normal distribution. Okay, so error term follows normal distribution means, in a simple plain words, okay, in a simple, to make it more easy to understand, okay, error term follows normal distribution help us to determine that the explanatory variable follows the normal distribution. When the explanatory variable follows normal distribution, then we can proceed with the hypothesis testing. In hypothesis testing, we know that we are conducting a hypothesis testing for a sample, not for the population. And for the sample, that explanatory variable follows the tree distribution, and they follow the tree distribution because we know or anticipate and believe that their population follows the normal distribution. And since that explanatory variable in their sample follows t distribution, we can conduct the hypothesis testing by referring to the t distribution table. But of course, the t distribution, normal distribution, they are pretty much the same. Even if you draw that t distribution, it will follow that bell-shaped curve as well. Yeah, so it's just a matter of differentiating the distribution from a sample with the distribution in the population. But in a simple explanation or in a brief definition, they are the same. Yeah, they are the same. Normal distribution, t distribution. It's just that that normal distribution is usually referred when we are talking about population, and the t distribution is usually referred when we are talking about sample distribution. Yeah. Okay. Are there any questions so far? Ada sebarang soalan?
No, sir.
Okay, sometimes I'm afraid if you are too quiet, I'm afraid that I forgot to switch on my microphone. But okay, I believe so far so good, kan? All right. What we have here. Okay, estimation of the, yeah, you can also put that thumbs up as a sign that you can hear and then you can see the screen. Thank you very much for that feedback also. Wah, banyak pula kan yang bagi thumbs up. All right. What is this? Estimation of the parameters of multiple regression through ordinary least square. Okay, so just like in a simple regression model, in a multiple regression model, the easiest way to estimate the relationship between explanatory variables with the dependent variable in a multiple regression is through the ordinary least square. This is the same. The reason why, the reason is the same as in a simple regression model, because ordinary least square is a blue estimator, best linear and bias estimator. Reason why the OLS is best linear and bias estimator is because they can produce the lowest value of error term. Okay, the lowest value of error term in a regression, which we can call as the residual sum of square. Later, I will show you that the result will be just as the same, okay? Just as the same with the estimation in a simple regression model, okay? All right. Of course, when we refer or when we conduct the, sorry, I need to charge my phone first. Sorry for that, yeah? Give me a few minutes, a couple of minutes. Sorry for this disruption. Let me switch off my camera first. Okay, where were we? All right. Of course, we know that we cannot simply estimate the regression model of a population because we don't have the entire information of a population. So we have to rely on the data gathered from that population through a sample, through samples that we have gathered. For that, okay, when we draw the multiple regression model from the sample, we can construct the sample regression function as in equation 4.3. So this is corresponds to equation 4.2, the population regression function. So here we have y, which is the dependent variable, equals b1. b1 is an estimator for beta 1 plus b2x2. b2 is the estimator for beta 2 plus b3x3. b3 is the estimator. That's why we call them, apart from calling them coefficient, we can also call them as estimator, because coefficient is usually referred to the population. X3 plus, here we have the residual, yeah, the residual. Of course, Apart from drawing the sample regression function corresponding to equation 4.2 for corresponding to the population regression function in 4.2, we can also have we can also construct equation 4.14. But basically 4.13, 4.14, they are the same. In here, in 4.14, we have the estimated dependent variable y hat equals b1 plus b2 x2 plus b3 x3 plus the residual. Of course, the residual equals the dependent variable plus b1 plus b2 x2 plus b3 x3. And this is the formula that we use to determine the residual sum of square. Yeah, the residual sum of square. And the residual sum of square is equal to the sum of squared value of y minus b1 plus b2. Sorry, this is supposed to be minus as well. Yeah, this I believe that I have made a typo here. This one's supposed to be y minus b1 minus b2 x2 minus b3. Same goes to equation 4.16. Y minus b1 minus b2 x2 minus b3 x3. Okay, sorry for that. Later I will make that correction. Okay. In estimating the B values for the OLS estimator, or in estimating the B value, which is the estimator for beta value, we will use or follow this equation. In estimating B1, we will follow equation 4.20, where here we have B1 equals mean y minus B2 mean x2 minus B3 mean x3 or x3 mean. Okay, so this is the formula that we use. Later I will show you how we calculate this based on example, don't worry. Okay, here we have B2 equals, here we have the sum of y times x2 times sum of squared x3 minus sum of y times x3. Remember, x3 is the second explanatory variable. Okay, times sum of x2 times x3 over, here we have the sum of squared x2 times sum of squared x3 minus sum of minus squared sum of x2 times x3. Seems quite a lot, quite complicated, but don't worry, it's actually pretty simple. Yeah, don't worry about it. Once you have done some practice, you will see how easy it is actually. B3 is equal to, here we have sum of y times x3 times sum of squared x3 minus sum of y times x2 times sum of x2 times x3. So we have that so many sum, isn't it? Okay, over sum of squared x2 times sum of squared x3 minus squared sum of x2 times x3. So just like in chapter 2 and chapter 3, that small letter y and axis denotes the deviation, okay, from the sample mean value. For example, the small letter y here equals y, which is the dependent variable, minus its mean value, y bar. Same goes to x, small letter x3 here. It equals to x3 minus its mean value. Yeah, and same goes to x2. Yeah, small letter x2 equals x2 in its capital letter, in its actual value, minus its mean value. Okay. So after we have estimated, don't worry, just like I said before this, I will show you the example later on. Okay, just today, sorry, in this part, I'm just going to show you the formula involved. Yeah, and I have shared you these slides as well, so don't worry about that. Okay, so here we have the variance in standard errors of the OLS estimator. So these formulas, they are very important for you to know, particularly in in conducting the hypothesis testing. Yeah, you need to know how to estimate the standard errors, because that standard errors is very important in estimating the t statistics. From that t statistic, we will then you can then proceed with the with the other components or other process of hypothesis testing. So here we have these variance in standard errors of the OLS estimators, means the variance in standard errors of the B1, B2, B3, as well as the variance in standard errors of the residual, or the variance in standard error of the regression itself. Yeah. So here we have the variance for B1, and it equals 1 over n. N refers to the size of the sample. If we have 10 sample or 10 observation in a sample, then n is equal to 10, 1 over 10. Okay. Plus, here we have the squared average value of x2 times sum of squared x3 plus squared mean value of x3 times sum of squared x2 minus 2 mean x2 times 2 times mean x2 times mean x3 times sum of x2 times x3 over, of course it will take some time. Yeah, it will take some time to calculate, but don't worry, yeah, they are not really that difficult actually. Over sum of squared x2 times sum of squared x3 minus squared sum of x2 times x3. Before I forget, here you can see that the denominator is the same in estimating B2 and B3, and not just that, it is also the same as in estimating the variance for B2, variance for B3, and variance for B1, variance for B2, and variance for B3. So once you have estimated once the denominator, you only have to refer to that exact value. You don't have to repeat in re-estimating the same thing. Okay, in counting the denominator. Yeah, all that you have to do is, of course, to estimate the denominator in B2, and then you can use that same denominator for B3, for variance for B1 until B3 also. Okay, so it is the same denominator, so you don't have to explain it, times the variance, yeah, of the regression, or the variance of the residual, right? So here we have the standard error for B1. Of course, standard error is the squared variance. Okay, standard deviation is the product of squared variance, just like the standard error. Yeah? We call it standard error because standard error is usually used to refer the standard deviation of a sample. This is explained in statistics. And then after that, we have this variance for B2, and it equals sum of squared x3 over the same denominator as you can see here, right, times variance, and then you square that to get the standard error for B2. For the variance of B3, so this is another typo, yeah, sorry for that, equals sum of squared x2 over the same denominator times variance. And in order to get the standard error for B3, all that you have to do is to find its squared value. Another thing that you need to notice is that in estimating the variance for B3, you can see that we are referring to the sum of squared x2. Yeah, sum of squared for x2. In estimating the variance for B2, on the other hand, we are using the sum of squared for x3 as a numerator. And this is the same as in estimating B2 and B3. you can see that the only difference, the only difference between in estimating B2 and B3 is these two components in the numerator. Here we have the sum of y times x2. And then after that, we have this, as you can see here, based on this pointer, sum of y times x3, right? And this is the same as what we have over here. Yeah, they are exactly, but of course they are their position is reversed. So here we have, in estimating B3, we have this sum of y times x3. And then here we have the sum of y times x2 on the other hand. The rest maintained. Okay, we maintain the rest of the component of the equation. Of course, here, if you are all aware, we have this variance of the error term. For sure, we will never be able to know the variance of the error term because the variance of the error term comes from the population, and we don't have the entire information to construct its value. So we have to rely on the residual error term. Sorry, the variance of the residual. So that is why we call them as RSS, the residual sum of square. Okay. So that is another name for the variance of the residual. So here we have the, of course, this residual sum of square is this one. Yeah, the variance of the residual is derived from the residual sum of square. Sorry for that misinformation. Okay, so RSS is not the same as the variance of the residual, but RSS is used to estimate the variance of the residual. So here we have the variance of the residual that is equal to, here we have the RSS, residual sum of squared, over n minus 3. And as I said before, this refers to the observation. Okay, still have many time. And if you can notice, before this, in chapter 2 and chapter 3, when we discuss the what we call as a simple regression model, we are using n minus 2 to represent the number of regressor. Yeah, including the intercept. Before this, we have two regressors in simple regression function. We have the intercept and the independent variable x2. Now we have x3 as the second explanatory variable. So in total, we have 3 regressors. Okay, we have 3 regressors. So we have intercept, estimated for x2 and x3. So that's why it's n minus 3. Okay, if you have 4 regressors, then it will be n minus 4. In that case, you will have 3 independent variable or explanatory variables, and of course you have the intercept as well. Yeah, so of course the standard error of the estimate will be the squared value of the variance of the residual. So a shortcut in computing the residual sum of square. This residual sum of square is important not just in estimating the variance of the residuals, but also in estimating the R squared. Okay, so here we have the residual sum of square, or sum of residual sum of square equals sum of squared y minus b2 times sum of y times x2 minus b3 times sum of y times x3. Okay, so here, as I said before this, that RSS is important in estimating the R squared. So this is the same as in simple regression model. R squared is equal to the what we call as ESS over TSS, the explained sum of square over total sum of squared. Yeah, ESS over TSS. This is the same as in chapter 2. Therefore, the same as I mentioned before this, the R square is equal to the RSS over sum of squared y. Right, so this r squared is equal to the RSS over sum of squared y. Sorry, not the RSS. R squared is equal to ESS over sum of squared y. That ESS, to explain sum of square, is equal to B2 times sum of y times x2 plus B3 times sum of y times x3. Okay, so this is the goodness of fit or coefficient of determination of the multiple regression model. Yeah, so this r squared is used to determine the percentage of variation in y that is explained by the model. So that is why we call them as the coefficient of determination. Percentage of variation of y, the dependent variable, explained by the model, explained by the regression model. So if we get, or if we square root the r squared, we will get the coefficient of multiple correlation. Yeah, this is used to determine the correlation between the regression model with the dependent variable. Of course, in estimating the correlation, we need to have a knowledge in terms of the relationship between the model with the dependent variable. Okay, that knowledge can come from observation. It can also be determined based on the theory. Means that in estimating the relationship, because when we talk about correlation, it needs to have a direction, either it is positive or negative. So in determining the direction of the relationship between the model, regression model, with the dependent variable, we need to refer either based on the observation that we have or based on the theory, what the theory said about the relationship. Okay, but of course, this coefficient of multiple regression is rarely used in a multiple regression, unlike in a simple regression, because in a multiple regression, you have multiple explanatory variable, and these multiple or explanatory variables, they may have different relationship with the dependent variable. Some will have positive, some will have negative. So how to determine the overall relationship between the model? The model means B1 plus B2 plus B3. Okay, their relationship, joint relationship with the dependent variable in a multiple regression will be difficult to determine. It's very difficult to determine. So that is why coefficient of multiple correlation is rarely used, even though it can be informative sometime on a certain perspective. Okay, so this, on the other hand, is the T statistics that we use to determine or in conducting the hypothesis testing of a multiple regression model. So here we have the T statistic for B1. T statistic for B1 is equal to B1 minus beta 1 over standard error of B1. So that's why I said before this, the formula that I've shown you before, this one, they are very important for us so that we can proceed with the hypothesis testing. And here we have the same, it is the same as the formula in estimating the T statistics for B2. Here we have B2 minus beta 2 over standard error of B2. And here we have the T statistic for B3 equals B3 minus, this supposed to be B3, sorry for that typo again, over standard error of B3. Okay, so sorry, I need allow me to. Sorry. All right. So here we have beta 1, beta 2, and beta 3. Of course, if we have 4 explanatory variable, then we will have beta 1, beta 2, beta 3, beta 4, and beta 5. Yeah, if we have 3 explanatory variables, then we have beta 1, beta 2, beta 3, and beta 4. But the formula, the general formula will be the same. And we also know that we will not be able to get beta 1, beta 2, and beta 3 as they are unknown. Otherwise, why do we have to estimate B1, isn't it? We simply refer to beta 1, beta 2, beta 3, and so on, right? Based on the information that we have on the population. So since we may never know the beta values, what we have over here is the expected or hypothesized value of beta. Okay, so sometimes, just like before this, our hypothesized value is equal to 0. So this is when we assume that the estimator that we have determined is not significant. So that is why it is equal to 0. So in that case, B1 minus 0. Yeah. So it depends on how we derive or how we construct the hypothesis statement. If the hypothesis statement state that beta 1 is equal to 0, so we will have B1 minus 0. If on the other hand, we are conducting a one-tail test and then after that, apart from that, or based on that hypothesis, one-tail test, we state that beta 1 is larger than 1, for example. So in that case, it will become B1 minus 1. Yeah. So it depends on that hypothesis statement. Later, I will show you the example. Okay, the step will be the same, in conducting hypothesis testing as in the simple regression model. Okay, so I hope that you have done your homework for chapter 3. Because this is almost the same as in chapter 3. We have a number of steps involved in conducting the hypothesis statement. In conducting the hypothesis testing. Remember before this, I said that hypothesis testing is used to determine whether we accept our estimation or reject our estimation. Yeah. So in step 1, we determine the hypothesis statement. In this process, we have to determine whether we are conducting a one-tail test or a two-tail test. I hope you still remember what we have discussed in statistics. We can explain much about that again, yeah, in this topic or in this session. So step number 2 is to determine the level of significance. Yeah, so that level of significance shows the percentage of us committing a type 1 error. So it is we usually use this alpha to represent the level of significance. And usually in conducting a hypothesis testing, we can either use 1% significance level, 5% significance level, or 10% significance level. So either 0.01, 0.05, or 0.10. After that, we will develop the t-statistic by following this formula. Equation 4.38 until equation 4.48. After we have determined the t-statistics, next step is to determine the t-critical value. Okay, in step 3, we determine the t-statistic. In step number 4, we determine the t-critical value. How do we get the t-critical value? We follow the t-distribution table. So that's why it's very important. That's why assumption number 7 is important. Only after the assumption number 7 is met, we can we can proceed with step number 4, because in step number 4 we are following that t-distribution table where the distribution is normal. Yeah, so that's why as I said before, this assumption number 7 is important in hypothesis testing, because without meeting assumption number 7, how do we conduct the hypothesis testing? Because we will never be able to know the t-critical value. The t-critical value that we refer on follows the t-distribution, yeah, which is normally distributed, of course, in general. Or if you, apart from determining the t-critical value, you can also determine the p-value, yeah, because both of these can be used to determine either we reject or fail to reject the hypothesis null. Yeah, remember, when the absolute value of t statistic is larger than t critical, we reject the null hypothesis and conclude that alternative hypothesis is correct. Vice versa. And when it comes to p-value, if we determine the p-value instead of the t-critical value, then we will reject the null hypothesis if the p-value is smaller, smaller than the significance level. For example, say that we're using the 5% significance level. Determining the level of significance depends on us, which level of significance that we want, if it is not stated in the question. Yeah. Say, for example, we use 5% significance level. And after the calculation, we determine that p-value is 0.03, which is smaller than 0.05 or 5% significance level. In that case, we will reject the null hypothesis and conclude that the alternative hypothesis is correct. Okay. So okay. This one later okay, it's okay. Maybe I can explain. Maybe I can explain this one before we move to the example. Yeah, I'll just complete all of these slides. Then after that, we move to the example. Okay. Because I have an example to show you how do we determine all that important informations. Okay, testing the joint hypothesis. So in multiple regression model, we can also determine whether the explanatory variables are jointly significant or not in explaining the dependent variable. In simple regression model, it's simple. We only have one independent variable and then one dependent variable. But in a multiple regression model, we have two variables or explanatory variable. Of course, we have one dependent variable. So apart from determining these explanatory variables, either they are significant or not individually in explaining the dependent variable, we can also conduct a joint hypothesis to see whether x2 and x3, the explanatory variables, jointly significant or not in explaining the dependent variables. So we can do that in multiple regression model. And there are a number of steps involved. Okay, so step number one is to form the null hypothesis, is to form the hypothesis statement. So here we have the null hypothesis statement stating that beta 2 is equal to beta 3 is equal to 0. It means that both of these independent variables, are not jointly significant in explaining the dependent variable. So that is why their coefficient value is equal to 0, because they don't have any impact or relationship with the dependent variable. Okay, so the good thing about the coefficient of determination is that, the good thing about coefficient of determination is that we can also use that coefficient of determination, okay, to represent the joint significance of the explanatory variable in explaining the dependent variable. It means that stating the null hypothesis as in equation 4.46 is the same as stating the equation as stating the relationship based on equation 4.47. Because in 4.46 we said that B2 is equal to B3 is equal to 0. So they are jointly insignificant in explaining the dependent variable. It is the same as saying that our coefficient of determination R square is equal to 0. Because remember, R square shows the variance of Y around its mean value. Okay, around its, the variation of, R square refers to the variation of Y. Okay, R squared refers to the variation of Y that is explained by our models. So when R square is equal to 0, it means that our model failed to explain the variation in Y. It means that our model our explanatory variable are not significant in explaining, are not jointly significant in explaining the dependent variable. So in simple word, 4.46 is the same as 4.47. Conducting the joint hypothesis based on this hypothesis statement is the same as conducting the joint hypothesis based on equation 4.47. So after we have formed the hypothesis statement, H null and H alternative, of course, step number 2 is to choose the level of significance, the 1%, 5%, 10%. Step number 3, instead of using or determining the T statistic, we will use the F statistic, because F statistic is used in determining the joint significance of the explanatory variables. Okay, so here we have this formula, simple formula. F statistic is equal to R squared over K minus 1. K is equal to the number of regresses. Remember, we have 3 regresses. Intercept, explanatory variable number 1, explanatory variable number 2. Yeah, intercept B1 and B2. Sorry, B2 and B3. So over 1 minus R squared time over N minus K. N is the number of observation or sample size minus K. So if we have 4 observation, or the size of our sample is 4, then it will be 4 minus 3, 1. Okay, so K is the number of regresses including the intercept, and N is the number of observation. Step number 4 is of course the same as in hypothesis testing before this. We determine or compare F statistic with F critical. If statistic is obtained through the F distribution table, okay, it is obtained through the F distribution table. In determining the F distribution, in determining the F critical value in the F distribution table, we have 2 degrees of freedom. First degrees of freedom is K minus 1, the number of regresses minus 1. If we have 3 regressor, it will become 2. The degrees of freedom number 1 is 2. And the second degrees of freedom is N minus K. Sample size minus the number of regresses. So if our sample size is 4 minus 3, then the second degrees of freedom is 1, or equal to 1. All right. So step number 5, reject H null if F statistic is larger than F critical. Yeah, if the absolute value of F statistic, of course, it will always be positive, then we reject the H null. Okay. But of course, if the F statistic is smaller than the F critical, we cannot reject the H null. Rejecting the H null, which is a situation when the F statistic is larger than the F critical, means that our explanatory variables are jointly significant in explaining the dependent variable. Okay. So another important thing that we need to know or important feature in multiple regression is the adjusted R squared. Remember, the R squared, even though it is important, but it can be influenced by the value of our explanatory variable. If we have higher values of explanatory variable, in other words, if we have many explanatory variables included in the regression model, our R squared tend to increase as well. It will increase as we increase the number of explanatory variable. So that is why we cannot solely rely on the R squared, because it is, if we can say, biased towards the number of explanatory variable. If we have multiple or many explanatory variable, then the R squared will be huge as well. It will lead us an incorrect impression that we have a very good model, even though in reality that R squared is not representing that we have a good model, but it means that our model have too many explanatory variable, perhaps. Yeah. So in a multiple regression model, rather than relying solely on the R square, we can also look into the adjusted R square. Yeah, adjusted R square is the adjusted R squared after taking into account on the number of explanatory variable. So the R squared is equal to 1 minus 1 over R squared times N minus 2 over N minus K. Okay, that one. So here the features of adjusted R square. So even though we are using this bar sign, it doesn't mean that this refers to the mean value of r squared. No, it refers to the adjusted r squared in this case. So if k is larger than 1, it means that we have multiple regression lah. Okay, because k refers to the number of regresses, or numbers of regresses. Then r squared, adjusted r squared, tend to be either equal if not smaller than r squared. Yeah, the adjusted r squared tend to be either equal if not smaller than r squared. That is the number of explanatory variable increases, then the r squared becomes increasingly smaller and smaller than the r squared. So in adjusted r squared, as we increase the number of explanatory variable, the adjusted r squared will become smaller and smaller and smaller relative to the r squared. Yeah, and it is not a surprise if our r squared is negative. Yeah, because it can happen that way. Yeah, based on depending on certain situation. Of course, if our explanatory one of the factors that can influence a negative r squared is when we have a large number of explanatory variable. Okay, so these are the important things that we need to know in the multiple regression model. Okay, it's formula to determine D1, D2, and D3, and the variance as well as standard errors apart from in conducting the hypothesis testing. Yeah, so I believe that it's better for us to take a rest for 5 minutes, and while we are taking our break, you can record your attendance. I will share you the link to the record to the attendance, shortly. Okay, so we take a break for 5 minutes. Yeah, I forgot to change my background lah. Yeah, it's a classroom background. Sorry for that. Okay, I will share you the attendance link shortly. So I will share it on the meeting chat. So while we are taking our break, if you have any questions, you can either put it in the chat box or you can also switch on your microphone. Feel free to ask. Feel free to ask, okay? Okay, good. If you don't have any question, hopefully you don't have any question because you understood all the things that I have explained just now. Hopefully. Okay, so I have shared the attendance link on the chat box or meeting chat. So you can simply click on the link to record your attendance, or allow me to share the QR code. You can also scan this QR code. Let me share it first. Okay. Yeah, so you can also try to scan this QR code to record your attendance if you cannot do so through the link provided. Thank you. So we take a break for 5 minutes, as I said. Okay, okay, let's continue. Let me share you my screen first. Okay, so can you all see the screen? Can you give me a thumbs up? Wow. We have 236 attendees. Yeah. You all supposed to be active lah. Ask questions ka. Okay. Okay, never mind. So let's continue our discussion on multiple regression model. So here we have an example. So based on this table, we have the we have the dependent variable indicated by y, and we have two explanatory variables, x2 and x3. So x2 is the first explanatory variable, while x3 is the second explanatory variable. And we have 4 observations. Or in other words, our sample size is 4. Yeah. So 1, 5, 9, 3 are the values for y, while 1, 3, 7, 9 are the values for x2, and 4, 2, 1 negative, and 4 negative are the values for x3. So here 1, 5, 9, 13 are the mean value. Sorry, are the value for y for a given value of x and 3. Sorry, x2 and x3 means that when x2 is 1 and x3 is 4, y is 1. When x2 is 3 and x3 is 2, y is 5. When x2 and x3 are 7 and negative 1, y is 9. And when x2 and x3 are 9 and negative 14 respectively, y is 13. Apart from that, we have this sum of value for y, which is 28. Sum of value for x2 is 20. And sum of value for x3 is 1. So here we have this summation notation here. Okay. Apart from that, we also found the mean value for y, which is 7. Yeah, so 28 over 4, 7. X2 is 5 in its mean value, while x3 is 0.25. Okay, so here we will learn on how to determine the estimators, how to calculate the estimator, and then proceed with the hypothesis testing. This is very important. Very important. Why? Okay, because in chapter 4, these are among the things that we need to know to estimate the estimator and to conduct a hypothesis testing. All right. So in helping you to conduct the hypothesis testing and in determining the value of the estimator, it is better for you to at first construct a table like this, similar to this, because this table will help you to determine the important values in estimating the numerator and denominator for the estimators for B1, B2, B3, and B4. Sorry, B1, B2, and B3, because we only have two explanatory variable. Okay, so in the table, in the table, we have another column. So this column shows the what we call as the product of y times x2. So here we have 1 times 1 equal to 1. And then, we have 5 times 3 equal to 15. 9 times 7 equal to 63. 13 times 9 equal to 117. So sorry, because we have to use this PDF because I cannot put them in PowerPoint because it's quite large in its size, of course. Okay, so another column to add is the multiplication. Yeah, ada sebarang soalan? Do you have any question? Kira-kira. All right. So here we have the multiplication of y with x. So y times x3. So y times the second independent variable. 1 times 4 is equal to 1. Okay. So 5 times 3 equal to 5 times 2 equal to 10. 9 times -1 equal to -9. And 13 times -52 is equal to 13 times -4 is equal to -52. Sorry, I have to saya kasih apa ni dulu, kamu silent kamu, because some of you here forgot to switch off your microphone. So I have to switch off your microphone first and then to switch it on. Okay. Hopefully that it will automatically switch off the microphone of those who forgot to switch it off before. Okay. All right. Okay, we proceed with our discussion. Sorry. All right. So here we have the sum of y times x2. Here we have 196 and y times x3 is -47. Of course lah, 4 times 10 plus 4 plus 10 plus -9 plus -52 is equal to -47. And then here we have the squared x2, means 1 to the power of 2 is equal to 1. 3 to the power of 2 is 9. Yeah. So squared 7 is 49. Squared 9 is 81. Its sum is 140. And then after that, we do the same for x3. I'm not going to explain, in details for x3 because it is the same. The squared product of x3 is 16 for 1 and 16, and its sum is 37. And then we have this x2. So what is this x2 in lowercase x? Just like I said before this, it is the deviation of x2 from its mean value. Okay, means that 1 minus 5 is the lowercase on the first observation. Okay, lowercase value. The lowercase x2 in its first observation. Okay, for 1 minus 5 is equal to -4. 3 minus 5 is equal to -2. Sorry, young those of you who forgot to switch off your microphone, kindly do so. to remove any noises?
Kamu yang kasih selera, aku yang kena.
Sorry?
Wow.
Ada yang lupa switch off microphone? Kindly switch off your microphone, please.
Lihat itu kamu punya sticky notes. Kau bani punca sebenarnya juga.
My goodness, I already informed you to switch off your microphone. It is not really a very, difficult thing to do. All that you have to do is to switch it off. Okay. All right. So we proceed. Yeah, we are running out of time. 3:26 already. We are dealing with microphone instead of discussing about multiple regression. Okay. We proceed with x3, lowercase x3. Here we have 3.75. How do we obtain 3.75? We subtract 4 with its mean value of 0.25 to get 3.75. 2 minus 0.25 is equal to 1.75, and you repeat the same process for the third and fourth observation. Here we have the lowercase y. We obtain that -6 by subtracting 1 to 7. 1 minus 7, -6. 5 minus 7, -2. Yeah. Of course, we have the mean values. The sum of lowercase x, lowercase y as well. Okay. And then we have the squared lowercase x2. Yeah. So -4 squared is 16. -2 squared is 4. We repeat the same process, not just for x2 squared, but x3 squared and y squared as well. Yeah. So 3.75 squared is 14.0625. For y, here we have -6, lowercase y. Its squared value is 36. So we have this next column, which is the sum of y times x2. So what does it mean by that is, we multiply x2 with y. So -4 times -6 is 24. Yeah. -2 times -2 is 4. We repeat the same process until the last observation. So this one, sorry, I pointed at the wrong column. Okay. For example, -4 times 6 is 24 positive. This one is the sum of y times x3. We do the same thing. 3.75 times -6 is -22.5. 1.75 times -2 is -3.5. We repeat the same thing until the last observation, and here we have the sum of x2 times x3. All that we have to do is to multiply x2 lowercase -4 with lowercase x3, 3.75 to get -15. -2 times 1.75 is equal to -3.5, and we do that same what we call as calculation for the rest of observation. Here we have the y hat, but in order for us to proceed with y hat, the residual, its squared value, and the rest, we need to at first determine our estimator for B1, B2, and B3. And since we cannot determine B1 before we determine B2 and B3, so we have to proceed with B2 first. Okay, so here we have the same formula for B2. And you can get this information from this table that you have constructed. So that is why it is very important for you to have that table constructed before you determine the B value. Of course, you can simply directly determine that, but the risk of committing an error or errors will be huge if you calculate it, manually, directly from the information from this value, raw value for y, x2, and x3. So that's why you have to. It's better for you to construct the table first. So here, because once you have the table, then it will be easy for you to determine the value of a particular components in the formula. For example, here we have B2 equal to sum of y times x2. This is equal to this. Yeah. sum of y times x2, 56. Easy for us to determine it this way. Times sum of squared x3. So sum of squared x3 is this one, sum of squared x3, 36.75, minus, so here we have sum of y times x3. Okay, sum of y times x3, negative 54, times sum of x2 times x3, this one, negative 38. Okay, that is equal to 6 over 40 times 36.75. This 40 is the sum of squared x2. This one 40. Okay, sorry, I have to explain fast because we are almost running out of time. Some of you have class after this. Times here sum of squared for x3. This one 36.75 minus, here we have the squared sum of x2 times x3. This sum squared negative 38. We have 26 as a denominator. So 6 over 26 is equal to 0.2308. That is our B2. An estimator for beta 2. The slope for the regression line of the x2, the first explanatory variable. Okay. And then we proceed with B3. We don't have to explain about the denominator because it is the same as before, 26. You don't have to waste your time to recalculate it because it is the same. Okay. All that we have to do is to change the value for this and this. To change means to flip their value. Okay. We multiply 36.75 with 54 right now, which is the sum of this one. The sum of y times x3, negative 54. And then here we have negative 56. It is the same as sum of squared value of y times x2. This is a typo. Yeah? This is supposed to be 56. It is not a negative 56, but a 56. Sorry for that mistake. Yeah, this is a typo. Let me correct that first. All right. Put an error sign there. Okay. Okay. So that is another thing. Another good thing about drawing a table. Easy for you to locate any miscalculation. So here we have negative 32 over 26 equal to negative 1.2308. Okay. And then after that, once we have calculated B2 and B3, then it will be easy for us to determine B1, because we know that B1 is equal to the difference between mean value of y, this, with B2 times mean x2 minus and B3 times x3 mean. So here we have mean y, which is 7, minus B2 times mean x2. So 0.2308 times its mean is 5, this one. And then minus again negative 1.2308, negative value, times 0.25, its mean value, 0.25 here. Okay, we have thus 6.1538. Okay, after that, after we have the B1, B2, and B3, then we can proceed with estimating the y hat, because we know y hat is equal to B1 plus B2 x2 plus B3 x3. By following that formula, yeah, B1 plus B2 x2 plus B3 x3, then we can estimate the y hat, because y hat is equal to that. Allow me to share you the formula for a moment. This, yeah, y hat is equal to B1 plus B2 x2 plus B3 x3. That one. So that is how this. Okay. Of course, in its mean, sorry, y hat. You're talking about y hat. This one, yeah. B1 plus B2x2 plus B3x3. So we follow this. We use the information that we have over here to determine the value for y hat. Okay, 1.4615, 4.3846, 9, and 13.1539. For example, for the first observation, we have 6.1538 plus 0.2308 times 1 plus negative 1.2308 times 4. That is equal to this y hat, 1.4615. We repeat the same process again for the second observation. To get 4.3846, we add 6.1538 with 0.2308 times 3 now, plus negative 1.2308 times 2. So we can get 4.3846. We repeat the same process for the third and last observation. Okay, then we proceed with the residuals. We know that the residual is equal to actual y with the estimated y. Okay, 1 minus 1.4615 is our residual, 0.4615. We have this negative sign here because in this case, our predicted y is larger than our actual y. We do the same for the second observation, 5 minus 4.3846 to get 0.6154. So here, of course, we have 9 minus 9 equal to 0. 13 minus 13.1539, we get negative 0.1538. So as I said before this, we can get the sum of residual. And the sum of residual is usually 0. It's close to 0, if not actually 0. Yeah. This is the good thing about OLS. It minimizes the residual value in our estimation. So that's why people prefer to use OLS, and we assume OLS as best linear unbiased estimator because it minimizes the sum of residual values. Of course, when you squared, we can get this. We can also square the residual, negative 0.4615 to get 0.2130. 0.6154 squared is equal to 0.3787. Of course, E squared is 0 squared is equal to 0. And here we have negative 0.1538. Squared them to get 0.0237. If we add this, we can get the sum of squared residual, which is equals 0.6154. And here, of course, since E is equal to 0, its sum of residual is equal to 0. If we multiply it, if we multiply it with the x2, we can get 0 as well. Yeah. This sum of E, which is the residual, times x2 and x3. Okay. So here we have this 1.8462. We obtain that by multiplying this negative 0.4615 with this negative 4 to get positive 1.8462. This negative 1.2308 is obtained by multiplying 0.6154 with negative 2. Yeah, we repeat the same process for the residual times x3 as well. Okay, after we obtain that, we proceed with our variance of the regression model, which is also the same as the variance of the residual. Okay, we obtain the variance of the residual or the regression model by dividing the sum of squared residual with n minus 3. As I said before this, we obtain 3 since we have 3 what we call as parameters, including the intercepts. Yeah, we have 3 regressors including the intercepts. That's why we subtract the sample size with 3 or by 3. So this sum of squared residual is 0.6154. That's why we calculate this. Okay, 0.6154 over 1, because 4 minus 3 equal to 1, we have 0.6154. So this is the residuals variance, variance of the residual, or the variance of the regression model. And then we squared 0.6154 to get its standard error, 0.7845. And then we can proceed with the variance for B1. Yeah, the variance for B1 is following this formula. Of course, we will replace the variance for the estimation with the variance of the regression. Yeah, so it means that instead of using sigma squared, we will be using the sigma hat squared, this value, because the sigma squared is representing the population variance. Since we are only referring to the sample variance, thus we replace the sigma squared with sigma square hat, or sigma hat squared. So here we have 1/4 times 5 squared. This 5 squared is the mean value of x2 squared. So this 5 squared times, here we have the sum of squared x3. So this is our x3, and its sum squared is 32, right? Plus, here we have the squared mean x3, 0.25 squared, times, here we have the sum of squared x2. So times sum of squared x2 is equal to 40. Sorry, this one. Okay. Sorry. This is another typo. Yeah, this is another typo. It's supposed to be not 140, because sum of squared x2, as in lowercase x2, is this one, 40, not 140. Sorry for that second typo. So another reason why it's better for you to construct a table first, yeah, rather than directly estimating the variance from the raw information. Minus 2 times at 5 times 0.25, you obtain that same information here. Minus, times negative 38. How do we get this negative 38? That negative 38 is the sum of x2 times x3. This one, negative 38. Over the same denominator, so we don't have to recalculate it, times the regression variance or residual variance, 0.6154, this same variance over here. Okay, we obtain 24.2071. So this is the variance for B1. We square root this 24.2071 to get 4.9201. We repeat the same thing. What we call as in estimating the variance. Repeat mean we do the same thing by referring to its specific formula and plotting each value in the formula based on the what we call a table that we have constructed. Okay, so the same denominator. Okay, the same denominator. Okay. And then here we have numerator, which is the sum of squared x3. So this is sum of squared x3, 36.75. Another typo here. Sorry for that. Okay. So times 0.6154, we obtain 0.8694. But I believe that this is an actual calculation, yeah, because I calculated this value based on the Excel, yeah. So I just plot this one just now, just before we start our lecture. So it means that this is an actual or correct value, but this is an incorrect or a typo, because this calculation is based on Excel. Yeah. All right, we square root that 0.8698 to get 0.9326. We do the variance for B3 by following this formula. Okay, so here we have sum of x sum of squared x2. So this is sum of squared x2, another typo here. Sorry for another mistake. Yeah, because I did not have enough time to recheck this example just now, because I created just before we start our class. All right, over the same denominator times variance of the residual to get 0.9467. We square root the variance for B3 to get its standard error. Here the standard error is 0.9730. Of course, we can proceed in estimating the R squared, which is the coefficient of determination. So here you can see that the coefficient determination follows this formula. Okay, and that formula is B2 times sum of y times x2 plus B3 times sum of x2, sum of y times x3. So that B2 is the same B2 that we have estimated before, this one, 0.2308 times 56. 56 is the sum of y times x2, this one, 56. This time it is correct. Plus B3, the same B3 that we have estimated just now. So that's why very important for you to determine B2, B3 first, and then B1 also. So here we have negative 1.2308 times sum of y times x3. This negative 54 here. Over the same thing, it is equal to 80. No. So this time, sorry, I thought it was a variance. This time we are estimating the R squared. So over our denominator here is the sum of y squared. The sum of y squared is 80. Okay, that is our sum of squared. Okay. You may experience lag in your screen, yeah, but you can watch the recorded session, because hopefully in the recorded session there is no lag in it, so that you can see, so that you can understand, you know, this discussion more clearly. All right, we have 0.9923. So this is R squared, and we can, since as I said before, this in a multiple regression, adding additional explanatory variable may influence the value of the R squared. We can conduct or determine the adjusted R squared, because the adjusted R squared take into account, yeah, the explanatory variables, or the number of explanatory variables that we have. So here we have 1 minus 1 minus R squared times n minus 2 over n minus k. So n is the number of observation. Here we have 4 minus 2 equal to 2 over n minus k. So k is the number of parameter. Thus we have 4 minus 3 equal to 1. So it is equal to 0.9769. Okay. So we have 4 regresses in our model. Yeah. Okay. So here you can see that the adjusted R square is smaller compared to R squared. This is as we said before. Yeah, this is as we said before. As we increase, okay, or in other words, if our regresses is larger than 1, then the adjusted R squared is either equal, if not smaller than the R squared. So here we have adjusted R squared that is smaller. Usually it will be smaller. It is quite rare for us to get an adjusted R squared that is exactly the same as the R squared, yeah, in a multiple regression model. Okay, so after that, after we have determined our B1, B2, B3, the variance and the standard error, we can proceed with the hypothesis testing. I'm not going to explain much about how we form the hypothesis, because that one we have explained. I have explained it before. Now our focus will be on estimating the t statistics. We know in hypothesis testing, if I can show you the process again. Okay. First is to determine or define the hypothesis statement. We have hypothesis null, hypothesis alternative. Oh, I forgot to share you the screen. Sorry for that. Let me show you my entire screen so that it is easy for me to, to change from slideshow to PDF. All right, so we know that in a hypothesis testing, first is to define the hypothesis statement. We have null hypothesis and alternative hypothesis. All right, and in step one, you also need to know that you also need to determine whether you are conducting a two-tailed test or one-tailed test. Okay, so I'm not going to explain more about that. I'm not going to re-explain that. After we have defined the hypothesis statement, in step number 2, we choose the level of significance, 5, 10, 1%. And then we develop the t-statistics in step number 3. Step number 3, we determine the test statistic. And this is the formula that is required. In estimating the t-statistics for B1, we use this B1 minus beta 1 over standard error of beta 1. So we know that B1 is equal to 6.1538. Yeah, so this minus the hypothesized value of beta 1. Remember, the hypothesized value of beta 1 is indicated in the null hypothesis. If we say that, or if we assume in the null hypothesis that beta 1 is not significant in explaining the dependent variable, y, then we say beta 1 is equal to 0. So that is our hypothesized value, beta 1 equal to 0, hypothesized value in the null hypothesis. So that's why here we have this hypothesized value 0, 6.1538, which is the value that we obtained before in this calculation. So here 6.1538 minus the hypothesized value for beta 1, 0, yeah, over its standard error. Standard error for B1 is this 4.9201. Okay, so 4.9201. Here we have t-statistics of 1.2508. Okay, we repeat the same thing for B2 and B3 in identifying their t-statistics. So here we have B2, which is 0.2308 minus its hypothesized value over 0.9326, its standard error for B2, this 0.9326. The same as the t-statistics for B3. So here we have t-statistics for B2 is 0.2474 and t-statistics for B3 is negative 1.2469. Remember, so here another typo, yeah, we're supposed to subtract with 0. All right, 0 because we assume that in the null hypothesis we assume that beta, in this case beta 2 and beta 3 is not significant in explaining the dependent variable. Yeah, so that is why it is 0. In this case, we are conducting a two-tailed test. All right. So after we have identified the t-statistics, step number, the next step is to determine the t-critical value or the p-value. We can refer to the t-distribution table. So let me show you a t-distribution table. Give me an example. Give me a moment. Okay, so this one. All right. We have identified the t-statistics. Now we look into the t-critical. Okay, t-statistics for B1 is 1.2508. In order to get its t-critical, first you need to know whether you're conducting a whether the level of significance is 1%, 5%, or 10%. Say we are using the 5% significance level, yeah, and we are conducting a two-tailed test. So this is the place. Why is it that I cannot share you the? All right, okay, right, this one, yeah. Okay, 5% significance level. We are conducting a two-tailed test, and our degrees of freedom is equal to n minus 3. Yeah, n minus 3. N minus the number of regresses. N is 4 because we have 4 observation minus 3, and then our degrees of freedom is equal to 1. Okay, 1 degrees of freedom, 5% significance level, 2 tail tests. Okay, all right. In that case, based on 1% degrees of freedom and 5% significance level in 2 tail tests, our T critical is 12.706. 12.706. That is our T critical. And we compare the 12.06, our T critical, with our T statistics, 1.2508. Obviously, in this case, our T statistic is smaller than T critical. What will we do if our T statistic is smaller than our T critical? We do not reject the H null. If we do not reject the H null, it means that we fail to conclude that beta 1 is significant in explaining the dependent variable. Okay, so for those of you who have another class to join after this, so you may leave, but for those of you who don't have any class, you may stay. Yeah, so for those who leave because of only if you have another class after this, yeah. For those of you who have to leave, or who has to leave, you can recheck or rewatch the video once I uploaded it. Okay. Okay, so we identified that D1 is not significant in explaining the dependent variable because T statistic apparently is smaller than T critical. We only reject if T statistic is larger than the T critical. Remember that. We do the same for T statistics. We do the same for B2. Okay, we know that B2, its T statistic is 0.2474. All right, so that is the T statistics for B2. And we identify its critical value. Of course, its critical value is this one. Yeah, 12.706. And it is smaller than the 12.706, also the T critical. Obviously, we failed to reject for B2, and in this case, we also failed to reject for B3 because when we look into the T statistics, we looked into the absolute value. So its absolute value is 1.2469, and 1.2469 is still smaller than the T critical of 12.706. In fact, even if we are using the 10% significance level, see here, 10% significance level, our T critical is still larger. Its T critical is 6.314 for this degrees of freedom of 1. Okay, so it is still larger even if we are using 10% significance level. Remember, as we lower our significance level from 10% to 5% to 1%, our T critical will become higher. Then it will be much more difficult for us to reject the H null because we are trying to minimize the risk of committing a type 1 error. All right, so here you can see in conducting the null hypothesis, in conducting the hypothesis testing by referring to 5% significance level, we failed to reject B1, we failed to reject the hypothesis null for B1, B2, and B3 as the absolute T statistic is smaller than the T critical. For that, we can conclude, or we cannot say that B1, B2, and B3 are not equal to 0. In other words, we cannot conclude that the intercept x2 and x3, our two explanatory variables, are significant in explaining the y. We cannot conclude that they are significant in explaining or influencing y. So that is what it means by, fail to reject the H null. If we manage to reject them, say for example, our T statistic is larger than 12, say 13. In that case, we say that that particular explanatory variable is significant in explaining the dependent variable y. Okay. So another thing, apart from using, as I said before this, apart from using the T critical, you can also refer to the p-value. You refer to the p-value. How to determine the p-value? Easy. Okay. Here we have the T statistics for B1, 1.2508. After we have this 1.02508, we refer to the T table. We know the degrees of freedom is equal to 1. Find a value that is 1.2508 in the table. 1.25. Here we see that 1.25 is between 1 to 3.078. 1 to 3.078. Okay, so that is where our T statistics is located. Yeah, 1.25. It means that our p-value is between 50% to 20%. Very huge, very, very huge. And if we are using a 5% significance level, we fail to reject the null hypothesis based on the p-value approach also, since p-value is larger than the significance level. Remember, our decision based on T statistics and p-value is different. T statistics approach is if the absolute T is larger, reject H null. P-value approach, on the other hand, is in reverse. If the p-value is smaller, then reject H null. One is larger, the statistic. One is smaller, the p-value. Here, our p-value is between 50%. Yeah, 0.5 means 50%. 0.2 means 20%. Yeah. Our p-value is between 50% to 20%. It is much larger than 5% significance level. Unless if our p-value is 0.01 and we are using 5% significance level at that time. So we successfully reject the null hypothesis. Okay. Another approach, apart from using the critical, apart from using the T distribution table, you can also use online calculator. Let me share you before we end our class so that at least you know how to use the online calculator, okay? Just you can simply type p-value of calculators online, okay? Let me share you the screen. All right. Okay. Right. Sorry for this advertisement, okay? Banyaklah advertisement kalau online ini. Alright, so we can determine the p-value from the T statistics or T-score. Okay, now in T-score we include or we key in the T statistics. Of course, we have three T statistical value because we have B1, B2, and B3. The three regresses. Okay. And we need to determine either these three regresses are significant or not. So here we have 1.2508. 1.2508. And then our degrees of freedom, remember, n minus k, n minus 3. So 4 minus 3 equal to 1. 4 regresses, 3, 4 observation, 3 regresses, sorry for that. And say we are using a 5% significance level in a two-tailed test. Okay, what is our p-value? Remember before this I said our p-value is between 50% to 20%. That's because we are using the t-table. Yeah, and in t-table we cannot pinpoint the exact value of p-value. Yeah, we can only guess the approximate location of p-value between 50% and 20%. If we're using online calculator, you will get this exact value. In this case, it's 42.9355%, which is quite true. Yeah, it's between 50% and 20%. Yeah, but in this case, it is much more accurate. So here, if we're using 5% significance level, we can say that B1, our intercept, is not significant in explaining the dependent variable y. We do the same for x2. So yeah, B2 lah. Yeah, 0.247 for 0.2474. Of course, this one is even smaller lah, kan? It is even smaller, so the p-value must be very, very high. Okay, so here we have 84%. 84%, obviously. So here we have 1.2469. So 1.2469. 69. All right, so 43%. Also higher, the p-value is higher than the significance level of 5%. For that, we fail to reject the null hypothesis, and we cannot conclude that x2 and x3 are significant in explaining the dependent variable. Okay, so since we ran out of time, you try to spend time to conduct or to see on how we can conduct the joint hypothesis testing. Yeah, so this one is considered as your personal homework or personal self-review. See and learn to conduct the hypothesis testing for joint hypothesis. Yeah, so here instead of using the T statistic, you're going to use the F statistics. You can look into the F value by the same calculator, but instead of choosing the p-value from the t-score, you choose the p-value from the F score. Yeah, F statistical value. Just type lah. You just type or p-value online calculator. I think you can get it. Okay. This one. In a p-value, you will have 2 degrees of freedom, numerator and denominator. First degrees of freedom is equal to n minus 1. Sorry. First degrees of freedom is equal to, let me see, I forgot to. K minus 1, n minus 1, K minus 1. The number of regresses minus 1. The second degrees of freedom is n minus K. Yeah, the number of observation minus the number of regresses. So I think that's all from me. Sorry because I took more than what is scheduled in terms of time. So sorry for that because I have to explain quite a number of things. So yeah, do you have any question before we end our session today? Ada sebarang soalan? I hope that you understood our topic.